Okay, so we're going to look at parent functions and transformations today. First thing we need to figure out is what is a parent function? So if you think about a family, and I love Disney and I love The Incredibles, so we've got a family here. The children tend to look like their parents. So they have similar features and you can tell they're related, but they're not identical, and there are some differences because you're combining two people to make one person. And so they've got similar characteristics, but they are different. So in terms of math, this plane has several parabolas up here in this picture. And so they have the same basic shape, a horseshoe, but they have different features too. Some are skinny, some are longer, some are fatter, some are opening wider, some are above the x-axis, some are below the x-axis. But just like their graphs are similar, so are their equations. So here they've got f of x, g of x, h of x, and j of x all listed out, and you can see how that affected their graph in the picture. So we're going to look at three parent functions primarily in Math 2, and the first one is a quadratic function. We've spent some time with parabolas so far, and so this is the parent function. This is the most basic that it could possibly get. It is x squared. And so you've got all of your characteristics that we've talked about so far over there. This end behavior would be up, up, so as x approaches negative infinity, f of x approaches positive infinity, and as x approaches positive infinity, f of x approaches positive infinity. Another parent function we're going to study is a square root function, and that is the square root of x. And so that end behavior, even though it's not listed, would be as x approaches 0, f of x approaches 0, so that's the left side, and on the right side as x approaches positive infinity, f of x approaches positive infinity, and all the other characteristics are listed out in that table. The last function that we're going to do a little bit with in this class is the inverse function, sometimes called the reciprocal function, sometimes called a rational function. And so all of your characteristics are notated over there. We do deal with things called asymptotes with inverse functions because there are invisible vertical and horizontal lines that graph is restricted by and that it doesn't typically cross. So, and we'll get to that a little bit later. So if we're just looking at the quadratic function to learn about transformations, we're going to start with your parent function over here in red and then a transform function over here in blue. And so remember your base function is x squared, so here we see that there's a negative in front. Well, what happened in this one? Well, we're going to type our response here. We see that it flipped over. So it went from being a u to being an n. And so mathematically what happens when there's a negative in front of the function or when a is less than 0, it's called a reflection over the x-axis. If we look here, same thing, we're going to compare the red function to the blue function. We've got x squared and then x squared plus 3. So what happened to that function? Well, it shifted up 3 units. So you can say shifted up 3 units. Or you can say it raised 3 units, whatever. Or it slid up 3 units, however you want to write it. It's up to you. We'll talk about the mathematical terminology in a minute. And so the same thing here, red to blue, we see that the red function, if we compare the vertex, moves down. And so if you've got a plus or minus outside of your function, if you've got the x squared piece that comes first and there's no parentheses, but you've got a plus or minus k, you've got a vertical translation, either up if it's plus or down if it's negative. Then here, if we compare the red to the blue, we see that it moves to the left. And so it moves 3 to the left. So here you notice that now my x plus 3 is what's being squared, not just the x. So we know that it moves to the left 3. And so here, if it's inside the function and it's subtraction, we see that it moves to the right. And so that's kind of weird because left is typically going in the negative direction. You'd have minus and right is plus. So those are backwards, so make sure you take note of that. So if we were to write it with the correct math terminology, we would say a horizontal translation. Sorry, I yawned. Horizontal translation, left or right. And remember, right is minus and left is plus. And then we've got a function. We've got a parabola, the parent function in red, and then we've got another really weird looking one over here in blue. It gets really, really flat or really, really wide. So we can say flattens, if I can spell it correctly, widens, anything like that. And so you'll notice there's a fraction in front of the x squared. And so I've got a video embedded here that you can watch on your own time. It's from Willy Wonka and the Chocolate Factory, and that's where Violet eats the, I think the gum, and she turns into a blueberry. So she gets really, really fat and really, really wide. And so what we call that is a vertical compression. And so that's when a fraction is in front of the function. So then, on the other hand, this graph gets really, really skinny or thin. And so that's a whole number in front. And so we call that a vertical stretch. So if you're still thinking about Willy Wonka and the Chocolate Factory, think about when Mike got really, really small in the TV room because he went from in person to in the TV screen. And when he came out of the Chocolate Factory, he was tall and thin. So if you have a number in front of your function, it's either going to be a vertical stretch or a vertical compression. With that, it's still your a value. So remember, we already know when a is negative, it's a reflection. And now we know that if it's greater than 1, so if it's a whole number, it gets narrower or skinnier, and we call that a vertical stretch. And if it's between 0 and 1, it gets wider, and that's called a vertical compression. So you can think about Charlie and the Chocolate Factory. And then, so those are all of your transformations. And so if we look at a couple of examples, we're given the equation and we have to write out the transformations, not given the graph, but given the equation, and we're supposed to figure out what the transformations are. So here we've got a 3 in the front, so we know when there's a whole number in front of the function, it's a vertical stretch by a factor of 3. We know that since there are parentheses, we've got a horizontal translation, and since it is addition, we've got a horizontal translation to the left 1 unit. And so everything else, the x and the squared, is what tells us that it's a quadratic function. It tells us that's a parabola. And so those are all your transformations. So if we look at another one, we've got a negative in front. That negative tells me it's a reflection over the x-axis. We've got another 4, so we know there's a vertical stretch by a factor of 4. And we know that we've got parentheses, so we know we've got a horizontal translation. Since it's subtraction, we go to the right 5 units. And then that minus 3, we've got a vertical translation. It's outside the function, outside of the parentheses, down 3 units since it's subtraction. So up and down is exactly what you think it would be. Left and right is opposite. If we look at the next one, we've got a negative in front. We've got a 2/3 in front. So that's all dealing with our a value. We've got an x squared, no parentheses, so there's no horizontal movement. And then we've got a plus 12 at the end of our function, so we do have a vertical movement. So first things first, we've got a reflection over the x-axis. Then we've got a vertical compression. We got an announcement coming. So we've got a reflection over the x-axis, then we've got a 2/3, that is between 0 and 1, and so we'll have a vertical compression by a factor of 2/3. And then we've got that plus 12, so we've got a vertical translation up 12 units. So moving on, if we are going in the backwards direction, if we're given all the transformations, we should be able to write a function. Remember that the base function is x squared in these circumstances, so sometimes we'll change it up when we'll use square root functions or rational functions, but here we're just dealing with the parabola, we're just dealing with the quadratic. So we'll start out with our f of x. A reflection over the x-axis when we've got a function is a negative in front, so we'll start with a negative. A vertical compression by 2/7, so we'll write that next. And then it's translated left. Since we have horizontal movement, we are going to use parentheses. Since it goes to the left, we will add, and then we will square it. So we've got a negative 2/7 x plus 7 squared. I'll make that a little bit bigger so you can see it. To get that squared function, if you are typing, since we are in Google Slides, if you'll hit the Control and the period button, it will make it a superscript for you. And then to get out of it, you would hit Control period again, and you'd be out of that superscript. If we look at the next example, I'll make mine a little bit bigger. Vertical stretch by a factor of 5 translated 7 to the right and 2 units up. So we'll start with our function. And so we don't have any reflection, so it'll be positive. Vertical stretch by a factor of 5 will come first. Since we do have some horizontal movement, we go to the right, so we'll have to have those parentheses. To the right is subtraction. So I have minus 7 and then squared. Same thing to get that superscript, you'll hit Control period. And then since we go up outside of the function, we'll have a plus 2. Next example, so last one of this kind, so we'll make it a little bit bigger for you. Reflection over the x-axis, so we'll start with our function, we'll call it f of x. It's a reflection, so we'll start with a negative. We've got a vertical compression of 4/5, and it's translated down, so we won't have any parentheses, it'll just be x squared minus 5. All right, and then in the next slide, we have a graph. And so compare the blue functions to the red parent function and identify the transformations. Well, first of all, between f of x and g of x, we can see that it does get a little bit skinnier and it shifts over to the left and down below the x-axis. So there's no reflections that take place. It's still a U shape. And so then we've got to figure out, well, we see that there's a vertical stretch because it's getting skinnier, but we don't really know how to figure that out just by looking at the graph. Well, good thing we've got the function here, that a value from ax squared plus bx plus c, that a value of 2 is going to be the same a value when we write it out in the other notation. So we'll have 2. We see that my function, if we compare the vertex at 0, 0, 2, negative 2, negative 1, we see that it shifts to the left 2 units, and that it shifts down 1 unit. So inside the parentheses, we'll have a plus 2 since we're going to the left, and we'll have a minus 1 since we go down. So you can look at it based on the graph. If we look at the next example, we've still got 2 functions. We are able to see that it flips over. We go from a U to an N. Remember, we're comparing red to blue. And then we also see that it gets wider. And so without having to do a whole lot of work, we can just look here at the function and notice that the beginning of my function is going to be negative 1/4. That's your a value. It's given to you. We don't even have to find it. And then we see we're going to compare the vertex. So we go from 0, 0, and then this vertex is at 8, 9. So we know we go to the right 8. So we'll have x minus 8. And we go up 9 units. And we're just comparing the vertex there. That's where that comes from. So that's basically what your homework is going to look like. You're just going to be comparing functions, and you will deal with some square root functions. So we're going to look at those next. So even though the base function might change, the transformations and their location in the equation look the same. So if it's a reflection over the x-axis, there's still going to be a negative in the front. This is what it does to your graph. So you've got a regular square root function, the parent function, and then if it's negative, you flip it over the x-axis. Same thing if we're going up or down outside of that square root function, you would have a plus or minus. If it's plus, it's up. If it's minus, it's down. Same thing about left and right. Oh, those shouldn't be squared. If you've got a square root function inside that square root or underneath that radical, you're going to have a minus h, which goes to the right, and you'll have a plus h, which goes to the left. So those are color-coded on the graph for you. And then finally, we talked about a vertical stretch or compression. And so if your a value is greater than 1, it's still going to be a vertical stretch, and that would be that blue function over there. And then if it gets wider, if there's a fraction in front, it would look like that green function. So same thing, even though we're dealing with all sorts of parent functions, all of the transformations will look the same when you're dealing with it in terms of the function notation. So if it's a reflection over the x-axis, it's still negative. So here we've got a rational function. If we put a negative in front, it reflects it over the x-axis, so it changes the quadrants that that graph is in. We can still move it up and down if you've got a plus or minus k outside of that base function 1 over x. If it's plus, we go up like the green one, and if it's minus, we go down like the blue one. Left and right functions the same way, so now instead of being parentheses, it's just in the denominator. And so we've got x minus h. Still remember your subtraction is to the right and addition is to the left. And then lastly, you still have a vertical stretch or compression. We won't deal a whole lot with those stretches and compressions in terms of rational functions, just because it is really tricky to see from the graph, and it's really funky to write a vertical compression with a inverse function. So just be aware of that. So those are your basic transformations. You got reflection over the x-axis, translated left, right, up, or down, and then you've got a vertical stretch or compression. So now you should be ready to practice and work on the homework.